performance of fading channel is very bad compared to AWGN channel. So how to enhance the performance of fading channel is the story today. So one technique is called diversity. If you do a diversity techniques, the performance of fading channel will be improved. Okay. So diversity mean we send the information independently faded path to the receiver, such that the probability of at least one of the path is better will be there. So we will the receiver is able to receive the signal. Okay. So the independently faded path can be a different time, or it can be a different frequency, or it can be different space as well. So that's called antenna diversity. So from transmitter to receiver, we send the same information independently faded channel such that at least one of the path will be good, and we will be able to receive the signal. So that's what is diversity basically meaning. So the main story, communication over fading channel has a poor performance due to significant probability the channel is in the deep fade. Okay, so deep fade mean, so let's say this is the channel quality versus time. Okay, the channel quality, sometime, as I said, the signal will receive constructively, so you have a channel quality very good, and sometimes it's go destructively, sometimes it's go like this. So let's say this is the threshold. So this is called deep fade. Okay, this is called deep fade. So during this deep fade, we may lose the information. So this is the case for the fading channel. Okay, this is the case for fading channel. Okay, but AWGN channel, we get bit rate due to noise, but most probably the fading channel we get bit rate due to deep fade. Okay, deep fade. Okay, so we need to do something about during this deep fading condition. So, okay, so that's what we are going to talk about. So communication over fading channel is a poor performance due to significant probability the channel is in the deep fade. So reliability is increased by providing more resolvable signal path that fade independently. So we try to send the information independently faded channel to the receiver. So basically, the probability of at least one of the channel is better is there. So we will be able to receive the signal. Okay. So diversity can be provided across time and frequency and space as well. So the time diversity, you need to do coding and interleaving. Frequency diversity is you send the information different frequency. Frequency selected channel have a frequency diversity already inherent in the channel. Space diversity is the one MIMO techniques. Okay, MIMO technique will provide space diversity. So name of the game is to how to exploit the added diversity in an efficient manner. Okay, as I said, in the frequency selected channel, the diversity is already there. And also the MIMO channel, the space diversity is already there. So the name of the game is to how to exploit the added diversity in an efficient manner. So let's compare the fading channel performance and AWGN channel performance. So AWGN channel, you may see this one in the basic digital communication course. The receive signal is a receive signal at the receiver. So you have a transmitter here, TX. You have a receiver signal here, a receiver here, RX. So this is AWGN channel. The receive signal Y is equal to X plus W. Okay, there's no fading. There's no fading. So there's no fading mean there's no channel coefficient in front of the. This is the transmitter signal X. This is the received signal Y, and this is the noise. Okay, so if you consider BPSK modulation, the the transmitted signal can be plus or minus A, and the probability of error is given by this Q function, which is given by square root of 2 SNR. Okay, SNR is signal to noise ratio, which is A squared over N naught. So this guy, this W is distributed as complex normal, zero mean, variant N naught. Okay, and so the SNR is signal to noise ratio is A squared over N naught. So the probability of error for the BPSK signal in the AWGN channel is given by this. Okay, so this is the Q function. Q function is a complementary cumulative distribution function. So the CCDF, complementary cumulative distribution function. This is Q function. So the QA, let's say, goes exponentially. Okay, decrease exponentially. Okay, Q0 is half, and Q1. Okay, you see Q0. The QA is defined as the probability x greater than A. So this is it's a normal distribution with the variant 1 and 0 mean. So this is 1 over square root of 2 pi exponential minus x squared over 2 dx. Okay, so this goes from A to infinity. So this is the Q function, and Q0 is half actually, and if you have a Q1, it is like a 0.159, and Q2 it is going to be like 0.00135. So why I'm writing this is going exponentially decay. Okay, this is exponentially decaying, and the probability of error for the AWGN channel is going to decay exponentially as well. For probability of error is going to decay exponentially with respect to SNR. Okay, so this is the main message for the AWGN channel. Okay, so the probability of error is Q square root of 2 SNR. SNR is sigma square, A squared over N naught. The Q function is the complementary cumulative distribution function of the zero mean standard normal distribution, zero mean variant 1, and the message is the probability of error decrease exponentially. Okay, that is the message. But if you will see soon, for the fading channel, the probability won't decrease exponentially. It will go 1 over SNR. Okay, so that is the problem. The probability of error for the fading channel is very bad. That's why we need a diversity techniques. Okay, so in order to prove this one, the next slide, how do we get this probability of error is shown in the next slide. Okay, so here the error probability decay exponentially with SNR. So that's what I said. The error probability decay exponentially with SNR. This is the case for the AWGN channel, and this is for the fading channel. Okay. So, so this is the Gaussian detection for the AWGN channel. Okay, so let's say there are two signals sent BPSK, UA and UB. So this may be a A, and this guy may be a, and this guy may be minus A. So plus or minus A is sent. The received signal PDF, if UB is sent, the received signal PDF is given by this plot here. Okay, if UB is sent, the received signal PDF is given in the right hand side. Okay, so left hand side. So this is the PDF if you send a UB. If you send a UA, this is the PDF. and if you send a UB, and this is the PDF, okay? So the receiver, if the receive signal is greater than this point, this is the threshold. If the receive signal is greater than this side, we choose, the receiver is choose UB is sent. If the receive signal is fall this side, we choose, the receiver will choose UA is transmitted. So this is the way the probability of error calculation normally happen. So I'll tell you. So the probability of error, so let's say, is given by the probability y is less than UA plus UB over 2, given that UA is transmitted, okay? UB is transmitted. So UB is transmitted, but the UB is transmitted, but UB is transmitted, Y is in the other side, then you make a probability of error. So this is exactly same as, okay, the probability, this is a received signal, Y is equal to X plus W. If the W is greater than UA minus UB over 2. So this is, so the UB minus UA over 2 is this guy. Okay, if the noise is bigger than UA minus UB, this is a mod here, or UB minus UA, whatever. So if this is the case, you make a error. Okay, if the noise is larger than this guy, so this is the UB minus UA. Okay, so half of that. If the noise is bigger than this, you make an error, okay? So this is the, I told you this W guy is the distributed as complex normal, 0 mean N naught. So probability of this is Q function. It can be UB minus UA, okay? So this is going to be UB minus UA over 2. So this is going to be, and we need to divide it by square root of N naught over 2. So this is N naught over 2 actually. So in this case, you will get UB minus UA is actually 2A over 2 N naught over 2 square root, and this turn out to be Q function to SNR. So this is the kind of a proof for the this equation. This equation. Okay, SNR is A squared over N naught. Okay, so if the W, the noise, is bigger than this value, it will flip the receive signal. Then you will make an error. So the probability W greater than this is a Q function. Q function is based on standard normal, but so that's why we need to divide by N naught over 2. So it turned out to be like this. So this is the way the probability of error is derived. Anyway, so let's say fading channel. For relay fading channel, the receive signal is Hx plus W. So the fading channel, so there is a transmitter here, and this is the receiver here, Rx, and this is the channel here. This is the channel here. The receive signal now written as Hx plus W. The receive signal is Hx plus W. H is the channel fading coefficient, okay? So again, same X plus or minus A. Coherent detection. What does coherent detection mean? The receiver, we assume the receiver know the channel. If the receiver know the channel, we say it's a coherent detection. If receiver does not know the channel, we try to detect the signal. That's called non-coherent detection. So coherent detection in all our wireless communication, your 4G, 5G, everything is work based on coherent detection. The base station and the users normally estimate the channel. Okay, so it's a coherent detection. Condition on edge, the probability of error is given by this expression here. Okay, so if you see the probability of error here, this term, the new term came here for the fading channel. If you for the AWGN channel, you see the probability of error. There's no fading coefficient here. It's 2 SNR. But for the relay fading channel, there is a channel coefficient. This guy is a random. This guy is a random. So I told you yesterday, this guy is a relay distribution. The squared magnitude is a exponential distribution. Okay, so this guy is a exponential distribution, random variable. Okay, we saw yesterday this H is relay distribution, and this H squared is an exponential distribution. So with the parameter 1. So if you do integration with respect to exponential distribution, and you will get probability of error is equal to this. Okay, so we have one tutorial question how to derive from here to here. It's a very complex derivation from here to here. So if you take average over h squared is exponential distribution. If you take average over x, that's exponential distribution, you will get this probability of error. And in the communication, we normally talk about high SNR regime and low SNR regime. Okay, so for in the case of so the probability of error goes here like this versus SNR. For the fading channel, it goes like this. This is the AWGN channel. This is fading channel. Okay, so this region is called high SNR. Okay, high SNR. And this region we call low SNR. Okay, low SNR. So in high SNR, you can show the probability of error is 1 over 4 SNR. Okay, so that's what I told you. This guy is reducing 1 over SNR, but here AWGN channel, the probability of error reduce exponentially. So we will see some question in the afternoon how to go from here to here and from here to here. So these are it's not easy to prove. These are very complex derivations. Anyway, so here is the relay fading versus AWGN performance for the probability of error. So you can see this is the probability of error for the AWGN channel. You can see it's decreasing very, very exponentially. For the fading channel, the probability of error is very bad. Okay, so there are coherent detection is here. Coherent detection assume channel is known at the receiver. There's non-coherent detection also. They are assuming there's no channel knowledge. Okay, so if you see 10 or minus 3, let's say 10 or minus 3 probability of error. For 10 or minus 3 probability of error mean you send 1,000 bits, only 1 bit is error. So that's mean 10 or minus 3. Okay, so for the 10 or minus 3 probability of error, the SNR required here is something around 7 dB for AWGN channel. Okay. Similarly, for the fading channel, if you go here, it is something like 24, something like that SNR. So there is a gap between. So if you go 10 to the minus 3, 10 to the minus 3 mean you send 1,000 bits, only 1 bit is error. For the AWGN channel, it's like a 7 dB. You need a 7 dB SNR. But for the fading channel, it's something like the 24 dB SNR. So the gap between here is something 17 dB gap in between. So 17 dB more power you need to get there's a difference between 17 dB. So 17 dB is very huge, okay? 3 dB mean you are doubling the power, but 17 dB is, it's a huge gap. So that's why we need a diversity techniques, okay? So to get a, 10 to minus 3 bitter rate, AWG channel need a 7 dB, but fading channel need a 24 dB. So there is a gap between SNR is 17 dB, which is very high. So we need diversity techniques to bring this guy very close to here. So the fading channel sometime even beat AWGN channel if we do some clever techniques. So that's what we are going to look at it. How do we bring this bitter curve closer to AWGN channel so how to bring the fading channel performance very closer to AWGN channel. So that's why we need diversity. Okay. So typical error event. So this is the probability of error for the fading channel. So if this condition happened, H squared is greater than 1 over SNR, error probability is very small. So this is the condition, we are not in the deep fade. Okay, H squared, the channel between the transmitter and receiver is very large compared to 1 over SNR, then the probability of error is very good. Okay, but if you see this condition, H squared is very less compared to 1 over SNR, we are in a deep fade situation, we will get the probability of large probability of error. So probability of this event, okay, probability of this event is we can prove in one of the tutorial question is 1 over SNR. As I said, this guy is distributed as exponential distribution. We can prove that is 1 over SNR. Okay, so the message of this slide is this condition is for good small probability of error. This condition for deep fade situation. In that case, we have a larger probability of error. So in the fading channel, we are getting error because not our noise is large. It's not like that. We are getting an error because we are in a deep fade. Okay, AWGN channel, we are getting an error because of noise is large. So there are two different situations for the error compared to AWGN and fading channel. Okay, so that's what it's saying here. Typical error event is due to channel being in deep fade rather than noise being large. So this is the good message, the story, important message of this slide, okay? For the fading channel, the typical error is due to channel being in deep fade rather than noise being large. But we get AWGN channel, we are getting a error because of the noise is large. But the fading channel, we are getting error because of we are in deep fade. Maybe I'll skip this slide. So, okay, so here is first I'm going to talk about time diversity. So what is time diversity? So anybody heard about Intelliver? Intelliver? Yeah? Did you heard about the word Intelliver? Okay, so what is this slide is saying? Time diversity can be obtained by interleaving and coding over symbol across different coherent time. So this plot is showing the channel condition between transmitter and receiver. Let's say there's a transmitter here, and let's say there's the receiver here, there's a channel here, okay? This channel, as I said yesterday, is a random. This channel is random. Take one random realization and stay for constant period. What that period is coherent time. And then take another random realization, stay constant period for coherent time, etc. So that's what is shown here. So take a random realization, stay constant period, which is the coherent time. This is the coherent time. And then take another random realization, stay constant time, coherent time, and take another random realization. So this is, we are in deep fade here. So here you see we are in a deep fade. and then take another random realization and to stay constant. Okay, so this is the way the channel behave. Okay, so if you send information from here to here, so here in this, okay, so normally communication, what happen is you have some image or video or whatever you wanted to send from here to here, base station user to the base station, let's say. You code those things, information, using LDPC or turbo code. So you have a code word. You send through the channel. Okay. So here there's no interleaver. You send that code word through this from transmitter to receiver. Here you are in a good channel condition. No problem. You will receive. Here also almost a good channel. You will receive. But here you are in a bad channel. So your entire code word is not going to be received here, and you will lose that code word. Okay, and then the next code word also we are in a good channel, we will be going there. So if we don't do any other clever techniques, in this case interleaver, if you don't do interleaving, that's why I'm saying no interleaving. This you are in a deep fade, you will lose the entire code word. Okay, but if you do an interleaver, so what does that interleaver mean? So let's say you wanted to send 16-bit, let's say your code word have a 16-bit, okay, let's say 1-bit, 2-bit, let's say 3-bit, up to 16-bit. You send this 16-bit through this channel. So this is your code word, okay? Without interleaving, you send this. But interleaver mean you put this 16 code word like this, 1, 2, 3, 4, 5, 5th bit, 6th bit, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bit. You arrange the 16 bit like this. You're not going to send serially 1, 2, 3, 4 bits to here. Instead of sending that, you send like this. You send 1 bit, 5th bit, 9th bit, 13 bit, and then you go back to 12 bit, 6 bit, 10th bit, 14 bit, and then you go back to, so you send like this. So you scramble the information like this. This is called interleaver. So you interleave and you send different order compared to this. So if you do an interleaver like this, okay, what happened is, this code word going through, there are, let's say, 4 portion of that code word going through different channel. So the first code word will first portion of the code word will go through this channel. The second portion of the code word will go through this channel. The third code word will go through this channel. The fourth portion of the code word go to this channel. By doing so, what happened is, this is the interleaved case. Okay, your all code word is divided by 4. One-fourth of the code word going through independently faded channel. Okay, that's what diversity means. You need to send the information through independently faded channel. So your entire code word is divided by 4 by interleaving and sent through independently faded channel. Okay, but here again you are in the deep fade. You will lose entire portion of the communication. But what happened here is, each of the code word, only 1/4 of the information is lost. Okay, here your entire code word is lost if you don't do interleaver. But here, if you do interleaver, each of the code word, 1/4 of the information is lost, and 3/4 of the information is received in your entire code word. That's good enough. If we use 5G is using LDPC and turbo code, these code words are very powerful code words. If the code word, if you lose only 1/4 of the information, this code word will correct. Okay, so only if you lose 1/4 of the information, does not matter. This LDPC code and turbo code will correct the information. So that's what this is called time diversity. So time diversity is achieved by interleaving and coding. Okay, so So your code word is going through independently faded channel such that even though you are in the deep fade, only some of the portion of the information is lost, and you will be able to recover entire code word using powerful codes like LDPC and turbo codes. Okay, so that's the message about time diversity. So time diversity is achieved by interleaving and coding. So coding alone is not sufficient. It's saying coding alone is not sufficient. You need interleaver as well. Here, you do only coding, but you need an interleaver to get the time diversity. Okay. So next, I'm going to talk about repetition code. So what is this repetition code is saying is, you send the information again and again in a different coherent time to get the diversity. So actually, this is repetition code is a very inefficient techniques because you need to repeat again and again, send the same information through independent faded channel. So by doing so, your spectral efficiency is very no good. So, but for the theory, people teach repetition code, but in practice, we are not implementing repetition code very often. Okay, so this is that's what I'm going to show you in the next two slides. Okay, so simplest code is called repetition code. After interleaving over L coherent time, the received signal is given by here. So repetition code, so you repeat the same information again and again for different independent faded channel. Then your received signal is given by this. Okay, so this is the vector now. Okay, this is the vector received signal, and this is the channel, and this is the noise. The same information is repeated L time. Okay, same information is repeated L independently faded channel, and you receive here. So here is the vector. This is the vector channel. Okay, so so the H is now is a vector H1 up to HL. Okay, so in this case, this guy is distributed as chi-square distribution with 2L degree of freedom. Okay, so so this is a very complex distribution. You will see in the tutorial the distribution is given for the vector channel. This guy is no longer exponential. Okay, only one variable, this is exponential. For the vector case, this is not exponential. This is a chi-square distribution with a 2L degree of freedom. And analyzing the performance for the vector channel, things are not easy. Okay, anyway. So this is a classical vector detection in wide Gaussian noise. So how do we do that here? So you have a receive signal here, Y, and this is your UA and UB, and you project this receive signal towards this, this line, and this is your Y tilde. This Y tilde is a sufficient statistics to detect whether we send UA or UB. Okay, so let's say UA is A into H, UB is A minus A into H. Okay, so the BPSK modulation. So your receive signal is projected through this line. And how do you do that projection? You multiply the receive signal by its channel complex conjugate divided by channel magnitude. So this is called Mach filtering. Okay, there are many names for this one. This is called Mach filtering, coherent combining, and receiver beamforming, etc. There are many names for this one. Okay, so this is, let's say, by multiplying the channel coefficient by divided by its magnitude is called Mach filtering. So this guy is a sufficient statistics to detect whether UA is transmitted or UB transmitted. Okay. So now in this case, so your received signal is y is equal to hx plus w. You multiply the received signal and you get y tilde by your conjugate over h into y. So by doing so, your equation is going to be like this. Okay, so it's going to be reduced to this equation. So this is this slide is this point is saying reduced to a scalar detection problem, and you can now detect. Okay, so by doing so, so how do we get this one? So how do I get this one? Because if you multiply by this, what happen is H Hermitian conjugate. There is Hx here. And this guy is nothing more than squared, and one of them is cancelled, and you get this equation. And we call this is as a tilde, W tilde, and W tilde and W distribution won't change. It's going to be 0 mean, let's say, n node over variant. By doing conjugate and divide by its magnitude, your distribution is not going to change. This distribution and the distributions are same, so the probability analysis is going to be not be affected by multiplying the conjugate of the channel divided by its magnitude. The distribution won't change. Anyway, so by doing so, I told you this guy is exponential chi-square distribution. So the chi-square distribution curves are like this. So if you have a so this H is now H1 up to HL, okay? So this, I told you this guy is now chi-square distribution with 2L degree of freedom. This plot is showing different distribution for different L, okay? So L is equal to 1 is the exponential distribution, and then L is equal to 2, this is the distribution, etc. And you can see the probability of error. I told you this is the condition to get the probability of error. The chi-square distribution can be approximated such that you will be able to prove the probability of error can be approximated as like this. Okay? So when you have a probability of error like this, the SNR to the power L, this guy, is called diversity order. So this guy is called diversity order. Okay? So if you have a L channel, your information is sent through different L path, so you get diversity order L. So this is the proof. Okay, so we have a tutorial question to prove this one as well. So this is the diversity order. Okay, SNR to the power L. When you derive the probability of error equation and you see what is the power of SNR, this will give you the diversity order. Okay, diversity order. So that means your signal is go through L independently faded channel. And then the probability of error curve looks like this. I told you for the fading channel that if there's no diversity, the probability of error goes like this. The slope is 1 over SNR. Here, the slope is 1 over SNR to the power squared. So the slope is 1 over SNR to the power 3. By doing diversity, you see we are bringing the probability of error curve closer to, towards at least to the AWGN channel. So by doing diversity, we are bringing this curve closer to SNR. So if you send information through different independent faded channel, you are bringing the curve closer to AWGN channel. So that's the proof here. The probability of error is 1 over SNR to the power L. So L is actually the diversity order. Okay, so I'll skip this one. So now next, I'm going to talk about any questions so far? Any question? Oh, yeah. Yeah, L is equal to 4. Yeah. Yeah. In that case, the diversity order is 4. Yeah. Yeah. Okay, so that's a good question. So you're asking which L is going to be, I think it's going to be a very large number of L. So yeah, okay, so yeah, it's going to be very large. Yeah. We can go and see. So you can see this is the AWGN channel. 10 to the minus 8 bit rate is like 12 dB or something like that. Okay, 10 to the minus 6 somewhere 10 dB. Okay, 10 dB. So if you go like that, so 10 to the minus, okay, 6 is 10 dB. So it's yeah, I think L is 5 is almost approaching. 10 dB, 10 to the minus 6, we are almost here as well. Yeah, we are here. Yeah, so any other question? So this is time diversity is the one I show you so far. Next, I'm going to move to the antenna diversity. So that's the interesting part, okay? So antenna diversity mean you send the information through, again, independently faded path, but by doing different antennas, okay? So this one is called receiver diversity. So you have 2 antenna at that receiver. So let's consider base station here. For 4G base station, or 3G base station, we used to have a 2 antenna. So here is a 2 antenna. Let's say 2 antenna, and let's say your mobile phone, okay, have 1 antenna. Okay, your mobile phone have 1 antenna. So you send the information from uplink information. It goes from 1 antenna to 2 antenna. This is called single input, multiple output case, SIMO channel. Okay, so in this case, your information that you send, you go through different independently faded channel H1 and H2. Okay, so this is the example receiver diversity. Okay, receiver diversity. As I said, your 3G base stations have used to have 2 antennas. In that case, uplink information is sent. You will get receiver diversity. Okay, so this is the SIMO channel, single input, multiple output. And let's say same thing. Now the base station is sending information to user. Okay, the base station now have a 2 antenna sending information to here. So this is multiple input but single output, MISO channel. This is called transmit diversity. Transmit diversity, multiple input, single receiver. Okay, here single input, multiple output. Okay, SIMO channel, MISO channel, and this. Let's consider your Wi-Fi router have a multiple antenna. Your laptop also have a multiple antenna. This is both transmit and receiver diversity. This is the one, the MIMO channel. Okay, so this will be, your information will go through differently independent fader channel. You get space diversity or antenna diversity. Okay, so let's talk about receiver diversity. Okay, so receiver diversity. So so how do we get this equation? So you have one antenna here. The channel is H1 here. The channel is H2 here. This is single input, multiple output channel. So your receive signal here, let's say Y1 is H1. You transmit X here. So X plus noise W1 at the receiver. And you have a Y2 here, go through the channel H2, X plus W2. And you put this as a vector now, Y1 and Y2 as a vector, and you have a vector channel H1 and H2 into X, W1, W2. So this is the one written as a Hx plus W. Okay, so that's the equation is written here. So this is the vector now, H is a vector and the W is a vector. Okay, so what we will do is, we assume receiver know the channel. We need to estimate the transmitted signal, which is X. What you do is a maximum ratio combining or match filter. How do you do that? You multiply the sufficient statistics to detect X is you multiply the received signal by its channel complex conjugate and divided by H. So this is called, this is a sufficient statistics to estimate X. Okay, so this is called match filter, maximum ratio combining, and there's another name, receiver beamforming. All are same thing. Okay, so in the book, people say match filter, and they say maximum ratio combining, coherent combining, and receiver beamforming. Everything is the same thing. You multiply the received signal by channel complex conjugate and divided by its magnitude. So this guy is a sufficient statistics to estimate X. Okay, so these have a different name. So this is the receiver beamforming. Receiver beamforming. Receiver know the channel and is multiplied by its conjugate and divided by magnitude, and you will be able to estimate X. So transmit beamforming. So let's say you have a so you, now we are talking about transmit beamforming or transmit diversity. So we have a multiple input, single output channel. So you have a 2 transmit antenna and single receive antenna. So this is you consider as a 3G downlink transmission. So this guy need to send some information, let's say X. It's do a transmit beamforming. It's similar to is multiplied by not conjugate, divided by this. This is and this is going to be a vector now. X1 goes through this one, X2 go through this one. Okay, so this is a small x, and this is X1, and this is X2. Okay, so you multiply the X by the channel. Here, transmit beamforming, we assume the channel is known at the transmitter. So how do we assume let's say you have a base station here, have a 2 antenna. You have a user, have a 1 antenna. Okay. So how the user know the channel between here to here? This guy will send the pilot signal, and from the receive signal, this guy can estimate the channel coefficient H1 and H2. So the receiver, so similarly, if it is uplink, this guy will send the pilot signal, from the pilot signal, the base station will estimate the channel. So receiver knows the channel is the good reasonable assumption. Okay, receiver know the channel is a reasonable assumption. That's what happened. That's called coherent detection. That's what happened in 3G, 4G, 5G. Okay, everything is receiver know the channel. But if you assume transmitter also know the channel, it is something more stronger assumption. How do we know the transmitter know the channel? So this guy send the information, pilot information, and this guy estimate the channel, and then it will feedback the channel to the base station. So this guy had to estimate the channel and had to feedback. So it involved more resources. He had to feedback the channel. So transmitter know the channel is some very strong assumption. Okay, but I'll talk later on. There are two modes of transmission. One is called TDD, time division duplexing. Other one is called FDD, frequency division duplexing. The frequency division duplexing, we need to do a channel feedback, estimate the channel, and you need to send it back. So FDD mode of transmission need channel feedback as well. So this is this consume lot of resources. You need to estimate the channel and you need to feedback. For in the case of 5G, okay, 5G we have a massive number of antennas here at the base station, and this guy estimate the channel between all the antennas to his own receiver, and feedback it is a lot of resources. Okay, so that's why in 5G all the base stations are operating at TDD mode, not FDD mode. But up to 4G, the mode of operation is mainly FDD mode, because the channel estimation and feedback is not that strong wastage of resources. So FDD mode of operation was, I'll tell you later on, FDD mean the uplink and downlink communications are different frequency. TD mean time division duplex mean uplink and downlink are the same frequency. Okay, if it is same frequency, there is a channel reciprocity is there. So TDD is a good mode of operation for the MIMO case. Anyway, so I'll tell you all these stories later on, maybe tomorrow morning. So now the message is transmitter know the channel is a very strong assumption. But to do a beamforming, we need to know the channel. Because we need information is X, you need to multiply by channel and divide by its magnitude. So this is called transmitter beamforming. To do that, you need to know this channel. Okay, so this guy need to estimate the channel, had to feedback to transmitter, then only this guy can do a transmit beamforming. Okay, so transmit diversity, if the transmitter know the channel, it will send this information like this, and then the receive signal, normally we write H Hermitian into X and plus W, and this H Hermitian is here. X is this guy, this is the H X, and let's say this is a capital X here, this is a capital X, let's say, into small x. So you will get H magnitude small x plus W. So now you will get the same equation as before to detect. So this is the way the transmit beamforming is happening. Okay. So here also maximize the receive SNR by in-phase addition of the signal at the receiver. So this is called transmit beamforming. This is called transmit beamforming. Okay, so it's reduced to scalar channel. This reduced to scalar channel here. So same as the receiver beam. This is the same as the receiver beamforming. Receiver beamforming also we get the same equation. So it's not here. So you will get the same equation. Okay, so these are the transmit diversity and receiver diversity. So let's see if transmitter does not know the channel, what happened. what happens if the transmitter does not know the channel? If the transmitter does not know the channel, it cannot do a transmit beamforming. Transmit beamforming, it had to multiply by the h and divide by its magnitude. It cannot do that. So in that case, in early 19, somebody called Alamuthi, okay, Suhas Alamuthi, he was working at AT&T Wireless in the west coast of USA. He come up with the techniques called space-time codes, okay. So that if you use that space-time code, then you will get diversity, but you don't need to know the channel, okay. So that's called space-time block code, okay. So this is very popular in early 90s because the 3G base station normally have a 2 antenna, okay. A base station have a 2 antenna, and it can do a space-time block code transmission to downlink users, okay. So I will maybe explain about the space-time block code after the break. Yeah, we'll take, yeah, okay. Yeah, yeah, okay.
Yeah, 11 o'clock, please join. And those who did not sign the attendance form, please sign. Anyone did not sign the attendance form?
Last, for the multiple input single output case, there are two channel coefficient H1, H2, and if the channel is known at the transmitter, you do a transmit beamforming, and X is the information that you need to transmit. You multiply the X by H and its magnitude, then we can show the receive signal Y. We normally write this way, and this is H Hermitian, and this guy is this guy, and this mean, and it will boil down to X plus W. So this is the transmit beamforming that we saw it, okay? So in order to do transmit beamforming, you need to multiply the transmitted signal by H divided by H magnitude of that guy. This is the vector channel, okay? So H here is H1, H2, okay? So this is the transmit beamforming. In order to do that, you need to know the channel at the transmitter, okay? So, but what happens if you don't know the channel? Then there is a person called Alamuthi, Suhas Alamuthi. He was in AT&T Wireless in the early 90s. And he come up with the techniques. As I said, transmitter know the channel is a big assumption, okay, big asking. So he come up with the techniques called space-time block code. Okay, it's very popular in the 3G era. When the base station normally have a 2 antenna and doing downlink transmission is done using space-time block code. So he come up with the space-time block code. This is going to achieve this. I'm going to tell you what is space-time block code in a minute. That space-time block code is going to achieve diversity, okay, without knowing the channel. So what is his techniques is, so you have a 2 antenna here, again a MISO channel, 1 antenna receive, and you transmit U1 here at first antenna, you transmit U2 at the second antenna at time 1, okay, at time 1. Then what you do is you transmit minus U2 conjugate at time 2 and U1 conjugate at time 2, and then you arrange the receive signal. So there is a receive signal Y1 at time 1 and then receive signal Y2 at time 2. So let's say this is H1, and this is, let's say, H2. Okay, so time 1, at time 1 is going to be H1 U1 plus H2 U2 and plus noise. Okay, at time 2 is going to be H1 minus U2 conjugate and H2 U1 conjugate and plus noise 1 here at time 1 and noise 2 at time 2. So then, so this is called space-time block code. Okay, space-time block code. Okay, you transmit 2 symbol at 2 time, but the second time when you send, you do something, conjugate, etc. Like this. Okay, so this is called space-time block code. Then you can arrange this receive signal Y1 and Y2 in such a way. Okay, you can rearrange these 2 equations that I wrote here. You can rearrange this equation like this in the first line here, and then you can also take a conjugate of the receive signal here, and you can put as a vector here. It will be you can write like this. Okay, the same equation you can rearrange. You take a conjugate of this receive signal and you can arrange like this. So what is you are seeing here? You know, once you do that, this column and this column are orthogonal now. This column and this column are orthogonal. If you take this column into this column product, it is going to be 0. These 2 columns are orthogonal. So that's what he did it. So by doing this conjugate and minus, etc., it turned out to be these 2 columns are now orthogonal. Okay? Then by projecting the 2 column of the H matrix, this is the capital S matrix, you can decouple this equation like this. Okay? Now you have a R1 H X1 U1 actually U1 some noise, and you can write R2 H U2 plus W2. Okay, U1 W2. So you can by doing this projection like a maximum ratio combining, you will be able to write these equation like this. Okay, by doing so, you can see now the U1 information, the information U1 and U2 is going through 2 channel because H is a vector here. It is going through both channel U1 and H1 and H2, and you will get diversity. So that's the Alamuthi scheme. Alamuthi scheme is just this scheme. You transmit U1 at the first antenna, U2 at the second antenna. The second time slot you transmit U2 conjugate and minus, and U1 conjugate, etc. By doing so, and you can rearrange the signal like this. Now this column into this column are orthogonal. And by doing projection, and you will get this equation. So the U1 go through this vector channel. So you both H1 and H2, you get diversity, and U2 also going through decouple and go through H1 and H2, and you get diversity. So we will do some question on how do we get diversity, etc. in the some of the tutorial question in the afternoon. So here, we are not repeating. We are, even though it's a 2 time slot we are using, but we are sending 2 information. So it is still, better than the repetition code. Okay, repetition code, what you do is you send same information again and again, but here we are in the 2 time slot, we are sending 2 information, U1 and U2. And one thing is here, compared to transmit beamforming, this guy will have a 3 dB loss in SNR, okay? Because transmitter know the channel, you can do a transmit beamforming, you will be able to get a coherent and combined receive signal that will give you 3 dB gain compared to here. Here we are not doing the coherent combining, so there is a 3 dB loss of receive SNR compared to transmit beamforming. Okay, so beamform, if the transmitter know the channel, you can do transmit beamforming. That will give you some SNR gain, but space-time block code, we don't know the transmitter. Space-time block code, we don't know the channel, so there is a 3 dB loss compared to this guy. Any question about space-time block code? So the 3G downlink, we are using space-time block code. So he become very popular, that guy, Alamuti. He came to UK and he become a Vodafone CEO for some time in UK, and now he went back to America as well now. So anyway, he was very popular in the 3G era. So then, how do we do space-time block code for more antennas? This is only for 2 antennas. If we have 4 antennas, but how do you do space-time block code? There are so much research happened in 1990 to 2000 and even 2010. There are so much research. People are trying to do the space-time block code for more than 2 antenna, 4 antenna, 8 antenna, etc. Yeah, you can extend to 4 antenna, but things are become complicated. So there are some results, space-time block code design. So this is the space-time block code. Some people derive a lot of results after that. So this is the space-time block code. So this xi that I'm U2 conjugate minus U1 and U1 conjugate U2. This is called a space-time block code matrix. Okay. A space-time code is a set of matrix. This set of matrix. So this results is for general, space-time block code kind of scenarios. Okay, space-time block code is a set of matrix xi. Full diversity is achieved if all pairwise difference have a full rank. So then people come up with a lot of theory behind these things, and they're saying the full diversity is achieved if the pair of different matrices are full rank. The coding gain is determined by the determinant of this matrix here. So there are a lot of results have been derived after this space-time block code came, okay, and then generalized to more antennas, etc., etc. So transmit diversity codes have a okay. So it is saying. So if you have a time diversity code, like a turbo code, etc., we can put a space-time block code like diagonal matrix, and then the determinant reduced to a product of a square product of the diagonal elements. Anyway, so that's all I wanted to say about space-time block code. But we will have some tutorial question on space-time block code later on. So I send you the slides and you forwarded to the students, huh?
Yes, I have forwarded to everyone yesterday.
Okay. So